So we are still in systems of what I call class 1, the conservative ones that look like x2 dot equals minus f of x. Now, just to to have it done, x dot is a shorthand for dx dt. X2 dots, it's a shorthand for the second derivative of x in time, okay? So x is a function of time, all right? And f of x is a given function. Okay, so which is equivalent with a first order system that we can write it in this way, okay? And now these systems have the wonderful property that they have an integral of motion, okay? That integral of motion, what it does, it stays, is like a function that stays constant along the trajectory of the system. So long story short, we know that this function, let's call it e of x and y, which in this case is 1 over 2 y squared. So I'll redo this theory from x naught to x of f of x dx is an integral of motion. And now I will write again what this means, i.e. if we do dE dt along any solution, so let's call along, let's put it for xy being x of t, y of t with this guy's solution, okay, so solution of, let's call it star, okay? So this is 0, i.e., no, I shouldn't have said that. Actually, what it means, not the D, that's how we verified, okay, silly me, okay. I.e., E computed along any solution is a constant, and it coincides, let's say, with E at time 0, or okay, we could put it x in t naught, whatever, initial time, y in t naught, okay? Where this is along any x of t, y of t solution of star, okay? How do we verify that something is an integral of motion? Okay, we verify this, so the fact that E of xy is an integral, let's write integral nicely here, integral of motion is verified or is implied or pops out by doing the following. Is verified by the condition, or is implied, not very, is implied, that's the right word, is implied by the condition, and the one that I wanted to write first time, dE dt along x of t, y of t, any solution is 0, okay? Because if a function is 0, its derivative is 0, then the function is a constant, okay? So in our case, okay, in our case, let's see how we do this. We would do d dt, I hope I have room here, okay? This would be 1 over 2 times 2y, y dot, plus, now the derivative of this thing here with respect to x, okay, and this is wrong. This, I should put a different letter inside and nobody says anything. Wake up. okay? Because we cannot integrate with x and then have x up there, right? Okay. So now we do the derivative of this term, right? So this would be f of x and then again x dot. So in this case, right, when we look at the system, this will be, okay, 1 over 2 is 2, just goes away. So it's y times y dot. So I'm looking at the system, yeah? Y dot is minus f of x plus f of x times x dot is y. Oh, and surprise, surprise, this is 0. And the fact that this is x of t and y of t is a solution is ensured that when I'm substituting this guy, so here I'm doing chain rule where I'm thinking that x and y are solutions of that system star. That's why I substitute these guys with the values that are coming from the star system. That's how we verify that something is an integral of motion, okay? So if I have an ODE system, okay, if you want, I can redo this philosophy. I'm gonna flip the page. So this is in general for any conserved quantity. So given, so I'll make it as an observation. If you have x dot equals, yeah, I'll do it like this, f of x and y dot is g of x and y. Okay, so I'm just saying, okay, so a quantity, or a functional quantity, because it's not a quantity, it's a function, okay? Let's say e of x, y, right? Which is defined on some domain, okay? To avoid I'm gonna rephrase to avoid to write the domain, okay? A real valued, there we go, function. So we know it takes values in R, e of x, y, is an integral of motion of, let's call this double star, if e of x of t, I'm going to write again this thing, is constant, is e of x at t naught and y naught, is like what we did the other page, for any x of t, y of t solution, okay, of double star. In practice, we need to verify that dE dt along a solution equals 0, i.e. that, okay, when we do dE dt, which will be df, right? So no, it's dE dx, right? X dot plus dE dy y dot equals 0. So basically we have to verify, I'm going to put this in a bracket, okay, that dE dt, dE dx, where now we substitute x dot with what is in the system, okay? So these guys, right, is like there. So we need to verify that the derivative of this E function along the flow of the system is 0. And this along the flow as words means practically when we do here the chain rule, right? Because this is what I'm doing here. It's a chain rule. I'm doing a dE dt along x of t, y of t. And now you'll know why you had homework, the chain rule. So this is dE dx, dx, dt, right? dE, dy, dy, dt. And now these are nothing else but dE dx, x dot plus dE dy y dot as notations, right? And then substitute x dot and y dot with what they are in the system. And if you get that that's zero, that means that this function, right? This function along the flow, the derivative of it is zero, and then thus the function is constant. Okay, that's the trick with these integrals of motion. Okay, and then I explained to you why they're useful, that we can, use them in two ways to lower the number of equations, or, to do the phase space. We did that, right? But I wanted to stress the how we look for integrals of motion in general, if a more general example. Okay, let's just put it like this. So for these systems, we know that this is an integral of motion because it's the nature of these systems. They're actually mechanical systems of 1 degree of freedom. Therefore, anyhow, we know that this would be an integral of motion. Is actually, and it is actually the conservation of energy. And again, we talked about this a little bit, but I don't want to stress the physics part of it as I want to stress the maths part of it. Okay, so there you go. Okay, so this being said, last time we started to do regions of motion, right? To discuss this. Okay, so I'm coming back to the general problem. So we had as the system of interest, fine, okay. And then we have 1 over 2 y squared plus integral from an x naught to x of f of s ds to be constant, okay. So I'm going to call this constant little e, okay. So now this, the presence of this integral of motion for this type of systems allows, so these guys, it allows the sketch of the phase plane, right? So it allows sketching the phase plane. Okay, so here is yet another example, right? We kept doing this, right? So the phase plane is xy, and then for this system we have 1 over 2 y squared plus integral from x naught to, so on purpose I'm doing this example like this, okay? So this would be 1 over 2 y squared and then plus 2s, because I want to talk about this bottom okay. So this is a constant, right? So IE, right, we would have the 2y squared plus 2x squared minus 2x naught squared equals, and not e, let's put constant, okay? And then thus we end up with something that looks like this, constant plus 2x naught squared, but this is a constant in itself. So I'm going to call this one to be E, okay? In other words, I'm leaving on the left-hand side all non-constants. And in the right-hand side, I'm just putting under the letter E, whatever constant, the constant that regards the initial time, if you want. So this would be a constant along any solution, okay? What constant, because I don't know how many times to stress this. What constant? Oh, so let's look, so for, let's say, for the solution that has, let's say, x in 0 is 2 and y in 0 is 5, the constant will be, what will be this constant? Oh, will be 1 over 2 times 5 squared plus 2 times 2 squared. So in this case, it will be 25 over 2 plus 8. You see what I mean? In this respect is a constant. Not that is a constant, the same constant for all solutions. Each solution has its own constant. Each solution has its own path. And along that particular path, the value of this combination 1 over 2 y squared of t plus 2x squared of t will stay constant. But the constant will be associated with that particular path. Each path has its own constant. Okay, so it's not like everything is a constant. Okay, fine. So now I'm coming back to the curve sketching. So face plane sketching. Okay, so in this case, we have this guy is a right, so it's constant. Then I said, you know, that I'm putting the name of this constant to be E, right? Some people call it H, but we'll use H for something else later. So how do they look, these guys? Oh, they will look like, we already did that quite a few times. They look like ellipses, right? That's one. We'll do this one, the center there. That's another one, right? So for each E, you have a different ellipse. So let's say this is for this one, right? Should be for E equals 1, okay? And these blue ones, let's say it's for E equals 2. I'm just saying, okay? And so forth, right? So each one. And this is the face plane for this oscillator. That's what it is. Okay. However, so I'm coming back to, okay, remember that this guy, okay, so that's how we wrote the thing, right? So this fellow here, this we call this the potential energy, right? And to be honest, what I'm going to call the potential energy, I'm going to call V of x to be just, okay, so the way we're writing it is, we should write it like, okay, really integral from x naught to x of 4 s ds, okay? But this is 2s squared from s naught to x, right? So essentially we get that 2x squared minus 2x naught squared. But now I want to convince you that we can just ignore this guy, this constant, because that one doesn't do anything in the equations of motion, right? So we'll just ignore it because it is irrelevant, okay, when, if you want drawing or sketching the phase space and when writing the equations of motion. Okay, so when we write the equations of motion, it doesn't even appear, right? Because it appears just x dot is y and y dot is minus 4x. Okay. It just appears, so y dot is actually dB dx of this v of x, right? So in this case is dB dx of integral from x naught to x of 4s ds, which is just 4x, right? Is that silly theorem in calculus that you did. I call the fundamental theorem of calculus. Okay, so now where am I going with this? Oh, so for this guy, okay, we have 1 over 2 y squared plus v of x equals constant, right? And where v of x is that 2x squared. Yep, that's what it is. I'm just rewriting. I'm going around the bush all the time. And then I was saying, last time we started to do, we say, okay, no, look, if we know v of x, and we are dealing with one of these 1D systems, we can actually determine where x, how big or small x can be. Okay, so I call those the regions of motion. Let's see. So what I'm going to do now, I'm going to just draw v of x first. Here, I'm going to draw it here. So it's a parabola, yeah? Okay. So here, this is y. I shouldn't put y. I'm just putting v of x, okay? And then, as I was saying, depending on the level of this constant, let's call it E, I will have some x's or some no x's, if you want. So this is v of x equals x squared, not 2x squared, 2x squared. So let's say what I mean. If I take a level of energy that is here, okay, nothing happens. Okay, so you'll say, how do you know this? Oh, let's recall what we did last time, right? So we did something, 1 over 2y squared plus v of x equals E. So 1 over 2y squared is E minus v of x, and this better be positive. So v of x better be always less than the energy level. And now I'm starting the discussion with the energy level. Right. So this condition tells us where x is allowed to be. What regions, or, well, regions, because usually people use this in higher dimensions. So, let's say interval on the x-axis is the solution x of t allowed to be as a function of E. Okay, so maybe this is awkwardly said, but essentially what we have to do now, it's always x, v of x has to be under the level of energy. That's the thing, under this horizontal line. So if I put the horizontal line here, there is no blue under it. There is no blue line under, nothing, right? So here there is no motion. There is no x. So there is nothing there, okay? In other words, if you look at it, you know, just if we're looking at this condition for this particular problem, which is, right? That's what I'm talking about, right? So if I take in this condition an E negative, there is no such E, right? Because here I have a sum of two positive numbers, so they can never be negative. So of course, if I take E negative, there is no motion, there is nothing, there is no solution, okay? If I take E now to be 0, okay, the only possibility for this is x of t equals 0 and equals y of t, by the way. So it's actually the equilibrium. Just looking at this one again. So here, look here. You have a sum of two squares to be 0. Each one has to be 0. And now comes the interesting one. Okay, so what about if we take a level of energy that is above now, right? So here is some E that is positive. And you know, the main condition is that, oh, we have to be with the function, right? Those values of x that are under this horizontal level. So only those ones are allowed to be. Oh, okay. So here they are. So x will play in between these two values. Okay, so let's say, right, I don't know, an A or B, or an x1 here and an x2 there. What are these x1 and x2? Oh, they are exactly the x's where these guys meet, right? So it's exactly where v of x equals e, right? That e. So it's exactly where 2x squared equals e. So it's exactly where x is root of e over 2 here. And this guy here will be x is minus root e over 2. I don't know if you can see. Let's see. Let's make them bigger. In this case, we can determine what is x1, right? So it's minus root of e over 2, and this is root of e over 2. And what is x2? So in a sense, what I'm saying now, we can do it like this. Okay, so in conclusion, why did I do this? I can say for e negative, there is no motion. For e equals 0, then x of t stays 0 for all t. And for e greater than 0, then x of t will always belong in between minus e over 2 and e over 2. And you're going to say, so what? Well, do you see what I'm doing? I didn't even solve the damn equation. I didn't solve anything. I just made a discussion. The only thing that I had to know is this conservation law and what is the potential actually. So just knowing what is the potential, I can tell you, what kind of motions to expect. And this is a silly example because it's very simple, but let's do one that is a little bit more involved. Huh? Let's do one that is like more, okay. So what about if we take, I have here an example, this one. There you go. Okay, where x is positive. If you look at it, this is another one of those x2 dots equals f of x, where in this case, f of x is 4, okay, minus 1 over x squared. Yeah. So how did, oh, they put a minus, right? Good. So it's good. I have the minus actually in the thing. Yeah. All right. Okay. So what is the potential? The potential would be integral from x naught to x of minus, yeah. I cannot put 0 because x is positive, right? But to be honest, again, when I'll work it out, I'll just drop the constant term. Okay, so what is the potential? So v of x, right, is, so I'm doing this integral here. So it will be 2 over x squared minus 1 over s taken in between s is x naught and s is x. So we end up 2 over x squared minus 1 over x minus 2 over x naught squared minus 1 over x naught. And again, I'm going to do the same thing here, the same stuff that I did before. I'm going to just drop this term. Because it doesn't do anything to the equations of motion. And then it's just a constant, this is just a constant that goes up and down the horizontal. It doesn't change the qualitative discussion that we're going to have. So while I'll show you how to compute the potential, then I'm telling you, okay, this part doesn't matter, the part from here on. So basically in this problem, we have the potential is this. Okay, so if I want to write the conservation of energy, so the integral, right? Energy integral, that's how we should call it actually. Okay, would be 1 over 2y squared plus v of x equals constant, okay? So in this case is 1 over 2y squared plus 2 over x squared minus 1 over x equals constant. Okay, that's one thing to do. Okay, so now we're coming back to the regions of motion. So for the regions of motion, I'll take this fellow and draw it and comment it, okay? So once again, okay, the reasoning is this one, 1 over 2y squared plus v of x equals e, from where we deduce that 1 over 2y squared is e minus v of x, which has to be positive, from which we have the main condition that this has happened. So in this case, we have that 2 over x squared minus 1 over x must be less equal than the decided level of energy that we're going to have. Okay, where we're going to have a discussion as the level of energy goes from bottom to the top. Okay, or we can do it the other way around, doesn't matter, like the energy comes from top to the bottom. All right, so first is first, we have to draw v of x. Okay, actually, and this is only for x positive, yeah? Okay, I should put it aside somewhere. Okay, so I don't need to draw the left-hand side, huh? X, okay. And now let's draw this guy. So I already know how it looks. It looks something like this, okay? Okay. That's v of x is 2 over x squared minus 1 over x. That's v of x there. Okay. And now this function, you know, when I'm calculating, this is a bottom here for the function, okay? And its coordinates are, so this is like the minimum of v of x. So you know how to find the minimum of a function. You take the derivative, you equate it to 0, right? Okay. So this baby here has coordinates. X is 4. So I'm going to call it x min is 4. And this is the minimum value of v, which is minus 3 over 8 for this example. Okay, so happy. And we start with the discussion. Okay, so let's pick a level of energy that is under the minimum. Oh, let's do it nicely. So this is E negative. So I'm looking what will be the important values. One is E negative. The other one is when it touches here, right? So this would be, right, E equals exactly minus 3 over 8. So it's exactly the value of the minimum of V. Okay, so I'm just picking up the important values and then, you know, I'll discuss one by one. Now, as I'm going up a bit, then here I'll have another level of energy that is in between. So let's call this pinky one E min, I guess, EM. So it's in between EM and it stops at 0. Okay, because in 0 again is changing. Okay. Then in 0, we have a fellow here. Well, I don't like this color. Let's pick another one. Okay, there we go. So this would be E equals 0. And maybe I should pick one more for E positive. So what we're doing now, we're just distinguishing between levels of energy for which the regions of motion are changing. They're not staying the same. So now I'm going to take it one by one and see what happens, okay? So for E negative, obviously there is no motion, okay? I do repeat to you, so the main condition is that the blue, I have to have blue under the horizontal line in order to talk about any motion, okay? So whatever X is allowed, the values of X that are allowing for the potential to be under the level of energy, those are the regions of motion for that particular level of energy. So for E negative, not E negative, for E less than EM, there is no motion. For E equals EM, there is one value for X allowed, and it's just the same one no matter what. We will have X of T equals X mean for all T, because there is no other freedom there to move around. Then next one, for E in between 0 and this EM. Let's see what happens here. This is the interesting part, right? I think. So here, X is allowed to be in this, right? Potential well, it's called actually, because it's like a well, right? So X is allowed to be anywhere in this interval here. So it will be a value here and the value here that are like the edge points of the allowed region, okay? So here, so that's where X can play in this violet segment, okay? And it could be, take a value from the left to the right. Okay, I have to put some names on this guy. So let's call this one an X1, and this would be an X2. But they depend on where I put the E, because if I put the E up or down, right, it will shrink or expand that interval, right? So if I go with E to a lower level, I'll have a lower interval, right? So it will be another X1 that depends on E and another X2, right? So it's one thing to take here, let's say we take here E minus 2 and here E is minus 3, right? So the value of X1 in minus 3 is a different one than X1 in minus 2. That's what I'm trying to say, okay? So it varies with the level of energy. So now I can say, okay, so for energies in between, this interval EM to 0, we will have that X of T stays bounded in between a maximum value and the minimum value, right? And these maxima and minima are really depend on the level of energy. How these guys are determined, if I will ask you a question like this, what are these guys? Oh, these are found by, solving, so they're intersections of E with the blue curve, right? These are solutions of V of X equals E. So in this case, there are solutions of 2 over X squared minus 1 over X equals E, where E is in between EM or 0, right? So I can see that there are solutions. Now I will not solve them to know what they are, but they can be determined, right? So they can be determined. They can be determined precisely. Yeah, as roots of that thing. Okay. Okay, and now we have for E equals 0. But to be honest, for E equals 0, it's pretty much the same as E is also, the energy is also above. Okay, let me go back to the greater equal than 0, because they're the same. So what happens here, no matter if I'm at 0 or above 0, the allowed region of motion, right, it's somewhere. So, you know, I'm doing it above 0 because it's easier. It's you see, it's all this, right? So I'll have a value of x that is a minimum value that starts somewhere. Again, it will depend on E. Okay, so let's call it x 1, 2, okay, x p of E, p from positive, okay? And, you know, it is allowed to be wherever in this, so it starts somewhere here if you want, okay? But then it's going to infinity, right? It can go as far as it wants. There is no bound to it, right? So it can be anywhere from this minimum value to infinity. So there you go. So x of t will belong to this xp of E to infinity, okay? And what is xp of E? Again, this is determined as root of 2 over x squared minus 1 over x equals E for E positive. So we already know it will have just one solution, that equation for E positive, because I can just see it, right? It's there, it's drawn. Huh? Of course, it would be much harder if we wouldn't have the picture, but the picture tells us. Okay. So I stress the fact that, you know, I deduce all this information without solving the equations. I don't even know how to solve this equation. I mean, remember here, where is it? Here, it was this one, huh? I didn't solve anything. The only thing I saw, I determined the potential, but the rest is just, well, you see what happens next. You know, from this information, we can actually draw the phase space. It's just like that. We can draw the phase space either from the energy directly or from the potential directly. Let's see what I'm talking about here. So here, I'm going to draw again the potential here. Okay. And then under it, I'll try to make a picture of the phase space. Let's see if I can. X, Y. Okay, so first the potential. Well, actually, now that I'm thinking, this can be higher, isn't it? Okay. Mm-hmm. And then what color is it? There's like a light blue, huh? And then I'll tell you what is this, what's this potential actually? What is it? Where is it coming from? Okay. So here, what did we do? We found the equilibrium here. Okay, so I'm gonna just put it down here. Okay. And then, I forgot what color. Okay, I'm trying to be consistent with the colors a little bit. So we had this level of energy here, right? So this was in between 0 and EM, right? So for this guy here, we have the bounds of X, right? We had the bounds of X there. And here how the story comes, you know, so basically we do know that the phase curve for this kind of systems are nothing else but the level sets of this function, right? Okay, so in this case, we have 1 over 2 y squared plus 2 over x squared minus 1 over x equals E, right? So I'm taking various E's and I'll have different profiles in the XY plane, right? So we can use Maple for that. You know, we can just open Maple and, you know, okay, do an implicit plot, you know, 2D with this thing or something, okay. All right, so, but without using Maple, just looking at these pictures, I can start, you know, reasoning the following. So this is the equilibrium, fine. Now, for this one, the motion is bounded, right? So X can be in between plus and minus something. and the phase curves are closed curves given by, right, this kind of equation. So basically y will be plus minus root of something something with x in it, right? Okay, so y will be, because this is bounded, right, in between a minimum and a maximum, because these guys are bounded in between a min and a max, y will be bounded in between a min and a max. So basically what we're getting here, we get like a closed curve. So for this level of energy, this is the curve we're going to get. If I change the level of energy to something smaller here, what will be? By the same reasoning, ooh, here, I'm going to get another closed curve there that corresponds to that level of energy. And if I increase the level of energy, I don't know, somewhere here, and I do the same reasoning, here is this guy. Okay, where is it? Oh, it's much further. It's out here, right? Here is another curve that corresponds to this one. Ooh, a picture emerges, isn't it? What about for h equals 0? Oh, for h equals 0, oh, now I'm in trouble here because okay, I have to redo this picture here. Okay, so let's do it. I'll need the 0 bit separately. Okay, so there's that. Okay, who's this? Okay, let's do it here. Okay, all right. So what about the level 0? Okay, level 0, I'll do it with black. Here is level 0 of the energy. E equals 0. Ooh, it's here. So what happened there? The trajectories escape to infinity. Okay, here it is. Whoa. Whoa. Okay, well, they shouldn't go down. They should just go up. Okay. Okay. Yep. That's what it is when you use the same continuous. Okay, there you go. So this is for E equals 0. What about for E greater than 0? Well, actually, they all go away, right? So if I take an E greater than 0 now, okay, right, here is its edge, somewhere here, and the trajectories are just going to infinity as well. And that's the picture that emerges just from the potential. Okay, can we put the arrows on this, like how the flow goes? Remember, this is, if you want the XY plane, is just a projection in the XY plane of what happens in time. So the third, if you think about it, the third axis is like perpendicular to the XY, and what you see, you know, projected down. So this trajectory is what they do, for instance, for this nice purple circle, what they do, you know, that's their purple. Okay, where is let's make a purple circle. So you have it in 3D, that's what I'm trying to tell you, okay? So here is your time, X and Y, and okay, where is it? It's somewhere on the x-axis, right? So here is your purple circle here, which is actually an ellipse or some closed curve, right? And what is actually happening in 3D? Oh, this corresponds to a nice cylinder, and the trajectories in time, right? They evolve on this cylinder, something like that, right? That's what it is actually. Okay, I don't know how to make it, right? That's in time, right? So this is in time. Whereas what we're looking at the projection down, if you want, okay? It's a bit loosely speaking, but it's a good thing to remember this. And what is that red dot, the equilibrium? Oh, that red dot is actually the solution that doesn't move its position in time at all. So it just stays there forever. Yeah. Okay. So now we need to put this arrow. So the arrows that we see as they move in time, they get projected down as well. So we have to put them here. So, you know, the question is, how do we know which way to put them? And I told you, well, we look at the system, right? Whatever, okay. But you see where y is positive. So from this first equation, y is positive implies that x dot is positive, so x is increasing, okay? This is like a really side note, okay? So where y is positive in the xy plane, x is increasing. Okay, so I have to put the arrows as x is increasing. You know what I mean? And once I put the arrow on the curve, it's clear what's good, because the arrows cannot come head to head. It's like coming with a solution from the future and from, you know, like we look here, it would come like from the past, and in the future would come head to head, which is not happening. It has to go the same way all the time. Once it starts one way, it's just going that way. Because otherwise, if you put the arrows head to head on one of this, it's like they would come head to head on that timeline, and that's not possible. So that's why I say it's sufficient to put one arrow, and then, you know, it's all they have to agree. Okay. Lots of information, huh? So I should tell you where these ones are coming. So what we drew here is the, instead of x, we can think that is the distance from the center of the Earth of a satellite. And that's how it evolves in time, actually. So you have this kind of orbits, but we'll do this in detail at some point in this course, okay? So, and also this potential is used also in molecular simulations for the distance in between two atoms. Okay, so that's one thing I wanted to mention to you today, or anyhow to discuss. The second stuff that we have to start, I'm sorry, I have to start. I would rather, you know, I would be happy to stop here, but, you know, I want to cover certain material before your assignment number 2. So, you know, I have to keep going. Okay, so the second type of equations, we call them second order damped. And I won't do much about them, but just introduce them today. Okay. So in general, you know, I would rather look at something like this. So this is a general format of a damped equation or whatever, but actually we are interested kind of a general form. In equations of the form x2 dots plus h of x, x dot plus g of x equals 0, or x dot equals y, y dot equals minus h of x, y minus g of x. So they have this kind of template, right? So this is written as a second order ODE. This is becoming in, you know, writing it in as a first order system, okay? And in particular, you know, this type of equations, they are showing up a lot in engineering and in applications, but their mother equation, if you want, is really the damped oscillator. That's why I call them damped equations. So here is what I'm writing here. Okay. So this is a model for an oscillator, like we did it before, like an elastic spring, if you want, or think of it, okay? So once we pull it out, yeah, there is the restoring force that we talked about, right? So this is some minus, I don't want to use K, so let's say Cx, okay? So that's the restoring elastic force, okay? So, you know, we talked about this, right? And then another thing that is here, if the velocity goes this way, so that's the velocity of this, so this guy goes this way, okay? The spring, you know, has some friction inside, you know, the material, okay? So that creates damping, or I like to call it friction actually, because that's what it is. Another way of damping is you can think that this is maybe a very light object that is flying through the air, you know, and there is resistance of the air, right? That would be another form of damping, right? So it's just the damping usually affects velocity, right? So it slows down the motion. So this damping force, right? So this, let's call it, did I put a damping on it? No, I call it friction, F damp, if you want, or and friction. Okay, so it's a thing, and it opposes the velocity. So it's minus K x dot, okay, where K is positive, right? So here C is positive as well. Okay, that's where it's coming from. So this is the template, right? So I'm going to write it again here. This is something that guys at physics probably do it, or they should do it properly. Okay, the full discussion. Okay, and I'm going to take omega positive. Okay, so that's, so if there is no damping, we hit the elastic, the harmonic oscillator. All right, so how do we solve these equations? That's why we had to do the ODE course. Okay, all right, so how was it? Now I'm going to write it as is written in the book, because I'm going to ask you to see all the solutions from the book, okay? Instead of omega squared, they use a C, letter C in the material, but it's the same thing. So if you remember, we have to build the characteristic equation, okay? And then we solve, right? So we have P1, P2, okay? So we have these roots. And then basically the solution is like, okay, so we have cases. So if K squared minus 4 omega squared, let's say, is positive, then we're going to have that P1 and 2 are real, okay? And actually we can write what they are. That's one. And then P2 is the other one. Okay, so obviously this is negative. You can prove that, so we're going to have a little discussion that this is negative as well. So I'm going to show you why in a second, okay? And then we end up with x of t to be C1 e at P1t plus C2 e at P2t. Remember? Okay. And then, you know, we have cases too. If this is negative, then again, you know, we're going to have that x of t would be C1 e at minus kt cos root of k squared minus 4 omega squared t plus a C2 e at minus kt sine of. So that's from the ODE course. This is why the ODE is required as a prerequisite for this one. Okay. But what we're interested here, we're not interested in solving this one, you know, I mean, that's beside the point. The point is that what is going on with these solutions? What do they do? Okay. How to interpret the solution. So for instance, for this fellow, okay, because this P1 and P2 are negative, if I want to see what's going on with any solution, I'll make a little graph here. Okay, so if I'm drawing them, no matter where I start, when I do the limit at infinity of x of t, this will be 0. Because we have here some exponentials with a negative power that are dying, right? So e at minus 3t is the limit is 0. So here, when I'm drawing these guys, no matter how I'm starting, I'm going to go down to 0. Maybe I'll go faster. Maybe I'll just have a loop, but I'll end up in 0. So in other words, our oscillator will oscillate, but it will die. Okay, actually it won't oscillate at all. It oscillates in this case, in the one under. In this one, it will just, you know, it just stops. Okay. Before doing the other one here, why is this number negative? Well, it's because k squared. Okay, so let's see how to do this. So let's say if I do k squared minus 4 omega squared is greater than k, this is k squared minus 4 omega squared is not greater, is smaller than k. Okay, which is obviously true, right? So this is true. So that's why, right? So this is less than k, and then you end up that this fellow up here is negative as well. That's why. Okay. So in this case, that is here, this is called strong damping, I guess. Okay, like there is no oscillation whatsoever. Whereas for this case, for this case, if we do the limit as t goes to infinity, this again will be 0 no matter where we start. But the difference is that for this type of damping, we will have some oscillation going on. So it's dying slowly, okay? That's the difference. Whereas this one is just going directly, okay? So I do invite you to read the full description in the module textbook, okay, where these cases are done there, okay, one by one. And yeah, I think I'll stop here today, and next time we're going to discuss stability and stuff, right? And stuff before you're dealing with it. Okay, guys, so I don't know. Okay, this is what I had to communicate today.